All right, welcome. Today, we are going to crack a classic linear algebra problem. We'll break it down step by step, and along the way, we'll uncover this really cool theorem that makes a seemingly tough question surprisingly simple.
So here it is, the big question that this whole thing revolves around. You take two subspaces, U and W, you mush them together to form their union, and when is that new thing still a subspace? It's a great question, and the answer, as we'll see, is pretty specific. Okay, so let's introduce our two main characters, U and W. They're both living inside the bigger vector space of polynomials that are degree 3 or less.
Now look at how different these two are defined. On the left, you've got U, and it's given to us as the span of three specific polynomials. Super straightforward. It's anything you can build from those three. But on the right, W is defined by a couple of conditions, a couple of rules that its polynomials have to follow. It's a totally different way of looking at it.
So before we can even touch the union question, we've got to get a handle on W. That definition is a bit abstract, right? So our first job is to decode it. We need to figure out what the polynomials inside W actually look like by finding a basis for it.
And right away, we get this awesome little simplification. Think about it. If you have two numbers, and their difference is 0, and their sum is 0, well, the only way that can happen is if both of those numbers are 0 themselves. So those fancy conditions are really just telling us that any polynomial in W has to have roots at both x equals 1 and x equals 2. See? Much simpler. So here's the game plan for breaking down W, step by step. We're going to start with a generic all-purpose polynomial. Then we'll apply our new, simpler conditions. That's going to give us a system of equations to solve. Once we solve it, we can find the general form for any polynomial in W, and from there, we can just pull out the basis. Let's do it. Okay, so applying those two conditions, p of 1 equals 0 and p of 2 equals 0, gives us this system. And when we solve it, look what happens. The coefficients a and b totally depend on whatever c and d happen to be. That means c and d are our free parameters. They're the ones calling the shots here. So we plug those solutions for a and b back into our polynomial, do a little rearranging, and boom. Look at this. Any polynomial you can possibly find in W is just some amount of that first polynomial plus some amount of that second one. It's all built from just these two. And this is the payoff. Those two polynomials we just pulled out, that's our basis for W. They can build anything in W, and they're linearly independent. So we've done it. We've decoded W, and we know for a fact that its dimension is 2. That's a huge piece of the puzzle. All right, we've done the prep work. We know U, we know W, we've got their bases. Now we can finally tackle the main event, the question we started with. Is the union of U and W a linear subspace?
And this right here is the theorem that changes everything. It's an absolute game changer. It says we don't have to go through the whole painful process of checking the subspace axioms on the union. No way. All we have to do is check for something much, much simpler. Is one of these subspaces hiding inside the other one? Okay, let's put this incredible theorem to the test. The name of the game is inclusion. We just need to figure out if U lives inside W or if W lives inside U. One of those has to be true for their union to be a subspace. Now, there are two ways we could go about this. There's the long road where we set up a big system of equations to find the intersection of U and W. It works, for sure, but it's a grind. And then there's the elegant shortcut, which uses the basis we just worked so hard to find. Just so you know, if you did take that long road and found the intersection, you'd find something pretty cool. You'd find that the intersection of U and W is just W itself. And if their overlap is all of W, that's just a fancy way of saying W is completely contained inside of U. But why do all that work? The shortcut is so much smarter. All we have to do is check our two basis vectors for W. Can we build them using the spanning vectors from U? If we can build W's entire foundation using U's building blocks, then it means the whole of W must be inside U. And check this out. It works. It's actually pretty clean when you look at it. The first basis vector of W is just 2 times U's first guy minus U's second. And the second one is a simple combination too. This is our aha moment. Since both of W's basis vectors are clearly in U, we've just proved that all of W is contained in U.
Okay, so let's take a step back and recap what we've just figured out. What are the big takeaways here from this whole journey?
So you see the path we took, right? We started with this mysterious subspace W and cracked its code to find a concrete basis. Then we use that powerful theorem to change the whole question from one about unions to one about inclusion. And finally, we showed that W is a subset of U, which means, yes, the union of U and W is, in fact, a linear subspace.
And that really leaves us with one final thought to chew on. This rule isn't just a one-trick pony for this problem. It's a tool, a new way of thinking. So the question is, how can you use this idea of turning a complicated question into a simpler one about inclusion to solve other complex problems you might run into? Something to think about. Thanks for joining.